What's up, everyone? My name is Dr. Chris Hacks, and today we're back with another CryptoPals Crypto Challenge, Challenge 11, an ECB CBC detection oracle. Now that we have both ECB and CBC working, we're going to be detecting which one is which. So basically, we're going to pass in some data, it's going to encrypt it with one of the two, and then we're going to figure out which one we encrypted it with without knowing. And there's a way to do that with the actual output from the function. So we're going to write a function to generate a random AES key, that's 16 random bytes. We're going to encrypt the data under the unknown key, and then it will basically be, we'll pass in our input and spit out some meaningless jibber jabber. Under the hood, we'll have the function append 5 to 10 bytes chosen randomly before and after the plaintext. And then we'll decide, 50-50 on which encryption algorithm to use. And yeah, it should be pretty simple. Since we're using C++, random is not necessarily built in like it might be in Python, so we will have to add a little bit of a helper function to help us generate some of this stuff. But nothing too crazy. So yeah, let's just jump right in. Alright, so I already have challenge 11 set up, and I already have the random.h header file here. So what we'll be doing is we're going to basically get a couple of functions to help us generate this data. So the functions we'll need are going to include random int. This will basically just give us a random integer, which we can use for the 50-50 function. So I'm going to use int lower bound and int upper bound. That way we can basically get a range, so you can put in like 1 and 0, and it's going to spit out either a 1 or a 0 every time. And you can use a range, and that will be useful later. I'm also going to get a string to generate random bytes. And then I'll make 2 of these. So first we're going to have one that you can actually pass in a single number into. That way we can generate, like 16 random bytes, for example, for our key. But we also might want a random number of random bytes. So we'll overload this function, just give it a different signature here, and what we're going to do is we're going to pass in a integer for the, we'll pass in an integer for the lower bound and an integer for the upper bound. And I guess for this length, I could probably just make it an integer. It doesn't need to be anything too crazy. Keep everything consistent. And what this will do is this will generate a random number, so like 5 to 10 bytes, which is what the problem talked about. And then get the includes, we're going to need string. And then also we're going to need a couple of C libraries for our random function. So we're going to use C standard lib for our random and include C time for actually seeding it. So if y'all remember, computers are not actually random. Anytime you pass in data to a computer, it can't just magically make up some random numbers. It has to run it through a function. Sometimes there's specialized hardware that can track like external factors. There's a couple different things. What we'll be doing is we're just going to take whatever time it is at the moment and pass that into our seeding function, and that will generate mostly random numbers. Not perfectly random, but it'll be good enough for our principle. Because we're not doing anything crazy with a random number. We just need about 50% of the time either CBC or ECB. So we'll do that. And then also we need to seed our function. So what that means is when we first start our program, we need to know, hey, have we already passed in the time or not? If we haven't, this Boolean variable right here will be false. But if we have, then we'll set it to true, and then we won't have to reseed it a couple of times. All right, so let's actually make this CPP file. So we'll call it random.cpp. All we have to do is include random.h. We have all our headers. And let me grab the functions real quick so we can go ahead and implement them. Alright, cool. So first for random integer, for all of them, whenever we call one of these functions, the first thing we're always going to do is check if it's seeded. So if it's not seeded, then we're going to seed it. So basically that means, oh, did I spell seeded wrong? Seeded. Alright, cool. Alright, so if it's not already seeded, if we haven't already passed in the time to our random object, we're going to do this. srand static cast, and then we're going to cast it to an unsigned integer, because that's what the function expects, or the object expects. And then we can just pass in the time. So std time, and then we have to pass a null pointer into here. And that just basically gives us, I believe that gives us the number of seconds since 1970. Or at least that's for Unix. Windows might be different, but it should be similar. Doesn't matter though. We're passing in a practically random number, which is what we need. Then once that happens, we can just set seeded equal to true. And now our function seed. And we're actually going to use this for every single one of our random functions, because we don't know like which order they're going to get called in necessarily when the program starts. So we just want to seed whichever one gets called first. We'll have it seed it first, and then it'll be good to go. It'll be good to use all our functions. All right, cool. So now we can just return a range. So what we're going to do is return lower bound plus standard random, and then we have to do the modulus of upper bound minus lower bound plus 1. So basically what this is going to do, say our lower bound's 5 and our upper bound's 10, this is going to return a number from 5 to random, and then this will be upper bound minus lower bound, which is 10 minus 5, so we have 5, plus 1 is 6. So this will return, the standard random function will return a random number that can be arbitrary. It's going to be any integer basically, and then we just modulus it by 6, and that will give us anywhere from 0 to 5. So we'll have lower bound plus 5 as our upper bound, so we can have anywhere between 5 and 10 basically. That's how this math works out. If you guys want to dive into that more, you can check it out. Go check out the CPP page for the random function, see how it works. But this will just return an arbitrary integer, and then we can do this math to get a number within our range. And these ranges are inclusive, so if we pass in 5 and 10, it will be a number from 5 to 10, and it will be an integer. Alright, for the string function, it's going to be similar. Let's actually generate random bytes first, the second one, because we're going to be calling this second function from this first function. So I'll show you that in a minute. So with our arbitrary range, we're basically going to be using the exact same logic here. So we'll just have length, alright, let me put it, int length equals this. And that's just going to give us that. It'll be arbitrary. And we can just make a string. And I'll call it random bytes. And it'll be length. And I'll just populate it with 0 for now. That way we get the string to be the right size. And then all we have to do is for auto reference byte in random bytes. What we'll do is we will get a byte that is just going to be it's just going to be a random character. So static cast char, and what we'll pass in is just std random modulus 256. That gives us the whole range of characters. That way we get every single character in the ASCII table from 0 to 256. It could be any of those, and it'll just populate our string with like random characters. We won't know what it will be. Return random bytes. And that's all there is to it. But that will pass in a random length, basically. So now we can just come back here and we can use this function to generate this. Just we know what the length is up here in the first generate random bytes function, we know the length. In the second one, we don't know the length. But luckily there is a very simple trick we can use. We just pass in the length that we want, and then we don't have a an upper bound. So let me show you what I mean by that. So standard string, and then what we'll do is we'll say random bytes length to 0, or what did I call it? It's called len. Alright, so all we have to do is pass that in, and let's take a look what the math will actually do. So we're going to have lower bound be whatever length it is, so say 16, and then we'll have upper bound be 0 minus 16 plus 1. So we don't want that. We don't want the negative. So instead, we'll just pass in length. And then if I do this math, it'll be plus 1. And yeah, modulus 1. So yeah, if we pass in length twice, then that means our range will literally be from 16 to 16. And yeah, that's what we want. Okay, so this will generate our random bytes. Oh, I'm sorry. I see what I did wrong here. This should still be 0. Instead, oh, what am I talking about? We don't even need to pass it in. We can just do the exact same logic here. Yeah, we don't need to complicate things. We can just use the exact same logic. We already know what the length is, so we're chilling. We don't need to do anything crazy with that. Yeah, so yeah, we'll just have this be its own standalone function. It doesn't need to call the other one. I was getting a little bit ahead of myself. So that should be it. We have a function that gives us a random integer within a bound. We have a function that gives us a random number of bytes, and a function that gives us a random number of bytes within a certain range of bytes. Okay, and yeah, I believe that should be it for our random functions. So now we can actually start working on our encryption oracle. And now the way this is going to work is we're going to use it twice, but that's it throughout the rest of the challenges, as far as I know. So I'm not going to make it its own function, like in terms of putting it in the encoding utils file. I'm just going to put it in challenge 11, and then I believe we'll use it in challenge 12 as well. So what I'll do here is we're just going to make our encryption function, encryption oracle, and we're going to put it in this file, like so. Okay, now it's pretty straightforward for what it does. So we're just going to generate a key that is 16 bytes. So key equals generate. Oh, I need to include random.h. That's probably important. Okay, generate random bytes 16. Okay, perfect. std string, let's add a ciphertext to hold our text, and we will have a string called plain text. What am I doing? I can just do this. Let me just simplify that a little bit. We'll have ciphertext, and then we'll have a string called plain text. Plain text, like that. Okay, and that's going to be generate random bytes, 5 to 10 random bytes. Well, yeah, that should be right. Plus the input, plus generate random bytes 5 to 10. Okay, cool. Perfect. So now we're getting our key. We have our ciphertext, and then we have our plain text, which is padded with 5 to 10 random bytes on both the front end and the back end. Okay, now we can just choose whether or not we want to use CBC or ECB. So I'm going to do if random int, and we'll do 0 to 1. That's going to give us a random integer from 0 to 1. It's equal to 0. So about half the time we will use ECB. So ciphertext equals AES 128. I need to include that as well, of course. Perfect. AES 128, called it ECB underscore encrypt, I believe. Yeah, that's what we called it. Okay, and then we can just pass in our plain text and our key. Okay, and then else ciphertext equals AES underscore 128 CBC, and we'll call it encrypt. Pass in our plain text, and we'll pass in our key. Cool. So that'll give us our ciphertext, and then oh, we do need to pass in an IV as well. That's right. If we do remember, the the challenge said use random IVs each time for CBC, so we'll just generate that. So td string, we'll call it IV equals generate random bytes, and we just need 16 random bytes for our IV. We can pass that in. We don't really care what it is because we don't care about the encryption. We just want to detect it. What else do I need? I need the block size, which is just going to be 16. Okay. You could make the 16s a constant and then pass them around, but it doesn't really matter for our purposes. In Enterprise, though, if you're doing a really big coding project, that's probably important, but here, it's not too important. Then we could just return our ciphertext. Alright, there is one more thing I want to add. Even though we are not supposed to know if it chooses ECB versus CBC, I'm still going to make a Boolean variable for it. So static bool is CBC equals false. The reason I'm going to have this is, even though we shouldn't really know, I just want to have an assertion that our program is doing everything correctly, just so it's easier for us to test and debug. But in like real life, if you're trying to break, ECB encryption, which is very possible to do, and you should never use ECB encryption in real life. But if you're trying to break it, you would not know if it's ECB or CBC or some other encryption scheme. Either way, I'm just going to have this here for our purposes. So that's going to be false, which is already true, and then this one's just going to be is CBC equals true. That way, we know later on. All right, cool. Now we can actually work on our encryption. So the way to actually detect this is we're going to look for repeated blocks with a input that is all the same. So like, say for example, I have a bunch of A's. I'm going to say like 48 or 64 A's. Then when it actually goes to encrypt it, ECB encrypts each block identically, while CBC will be a little bit different. So if we remember, each block is 16 bytes. We just need a couple of 16-byte blocks. So I'll do that. So let's do a string. And we'll say, call it plain text. We'll say it is, let's do 4 blocks worth. So 64, and we're just going to have the character A. Okay? Now, what we'll do is we're going to go through and we're just going to test our oracle here. I'm not going to output anything like anything crazy. Like, I'm not going to output the oracle code. We're just going to use this assertion that we have from earlier. So 4, let's do it, let's see, how many times do we want to test it? Let's say we'll test it 120 or 1024. So that's the power of 2, so we'll test it that many times. That should give us a pretty good sample size. We'll have a string called ciphertext. And then we'll pass in plain text. And then the way it should work is that for ECB, all of the blocks should be different. Now, there is like a really rare case. It is potentially possible that the randomness doesn't line up correctly, the stars don't align perfectly, and we do get something that is going to be 2 blocks are identical. However, that's very, very unlikely, so it shouldn't be an issue here. It could happen, but it shouldn't. So if you guys do see a fail, run the code again. And if you see a fail again, then it probably is some sort of coding issue. But if you see it once and then it passes like 5 times in a row, we probably just got super unlucky. However, let's see what happens. Because basically what we're going to do is if we're going to do our little check here. So I'll just put true for now. I'll use a placeholder. We're going to check. And if our check passes, if our assertion passes, then we'll just continue. However, if our check fails, so else, then we will return fail. And then that's basically what we're going to be doing. And then if everything passes, we can just return pass. And yeah, so that's what we're going to be doing. Basically, we're just going to check, hey, did our detection work correctly? Did it detect the right encryption schema? And if it didn't, then we'll just mark it as failed, and then we'll go back and figure out what's going on. So in order to detect CBC versus ECB, all we have to do is this. Has repeated blocks. Oh, I need to include our encryption utils. What do I call it? It's called encoding utils. That's right. Okay, we'll include that. So if has repeating blocks, and then we'll pass in our ciphertext, and we have a block size of 16. If this is true, then we have detected ECB mode. And then we also have an XOR with is CBC. So if this is true, then is CBC needs to be false. And if is CBC is true, then this needs to be false. So that's how our logic works. Okay, so that should be it. Let's go ahead and run this and see what happens. Make sure everything runs correctly. Okay, it's compiling everything. Okay. Okay, it's running. Might take us a minute because we are encrypting and we are encrypting, 1,000 times in a row, so it's going to be a little bit slow, but we do want to have a good sample size. Okay, let's see here. It is taking a little bit to run through all this. Oh, maybe our sample size is too big, huh? This is taking quite a long time. Wait, did it? Oh, unexpected error, of course. Of course. Let's see what happened. That's why it was taking forever. Alright, so as per usual, we will be doing a little bit of debugging. So let me debug this real quick, and then I will get back to y'all. Alright, I'm back. So here's what happened. I've had problems with this before, but it did have to do with the padding. Since we did turn off the padding in the actual functions using their padding, and we're using our PKCS7 function instead, we do have to do a little bit of magic. So what we did here, anytime the AES encrypt function is called, I'm going to make sure we pad our data properly. And inside ECB, it is also padding the data. So what I can do is I'm actually going to undo this for CBC as well. So let's just go ahead and test it. What I recommend doing is, you guys should test this on your own, but inside of our AES encrypt function, we're going to pad our data, and then we're going to unpad it when we actually go to decrypt it. Okay? So I recommend testing it. I'm going to test this thoroughly just to make sure I'm giving you guys good information, and then I'll remove the CBC encrypt padding. Okay, after a little bit of thought, it should be okay if we pad our data both here and inside our AES function. The reason why is because our function, our PKCS7 function, is only padding the data if it's not a modular, if it doesn't fit into the block size easily. So let me show you real quick what I'm talking about. Encoding utils. So basically, if I go to the function definition, if the final block length is equal to 0, then we're not actually going to do any padding. Okay, so it should be okay. So if we pad it multiple times, it will still have the same output. It is a little bit less efficient, but it should be fine. So with that being said, come back over here to challenge 11. Let's go ahead and run everything. And it should all work correctly. Yep, and we get a pass. So that's why it should be that quick. The reason why it wasn't earlier, because it hit a breakpoint, because it failed. But yeah, so now, because it passed, that's what we needed. That's what we wanted. Feel free to check this out and test it out more yourself, because it is a great learning experience to see like what's causing it to pass and what's causing it to fail. A little bit outside of the scope of this video, because I don't want to make it too long, but thank you all for watching. I'll see you guys next time in the next video, and make sure to keep coding. So yeah, see you guys next time.